Welcome to GTC. My name is Pen Lee. I've been working on the open source inference frameworks at NVIDIA. I'm happy to let you know that I'm the chair for this session. Before we begin, I've been told to make a few housekeeping announcements. First one is, check out the GTC brain dates, connect with fellow attendees through curated one-on-one or small group conversations, browse the topic market to brainstorm, solve challenges, and share expertise. Book through the GTC app or find out more at the GTC Brain Date launch at the Tech Interactive. Second one is my favorite. Make sure you check out the GTC Park, where you will find our installations, launch areas, food trucks, and sponsor activations, as well as our vibrant night market, open from 7 to 9 p.m. Hi. So the first speaker today is Omar Gedas. He's a professor of mechanical engineering at the University of Texas at Austin, who holds the Cockrell Chair in Engineering. He's also principal faculty and the director of the Optimus Center in the Odin Institute. His research focuses on theory and algorithms for large-scale Bayesian inversion and stochastic optimal control design for complex engineered and natural systems. He's a three-time winner of the ACM Gordon Bell Prize, a recipient of the CM Geosciences Career Prize, and the CM Babushka Prize, and a fellow of CM and the UCACM. The second speaker here, Stefan Henneking, is a research associate at the University of Texas at Austin. In his work as a research associate at the Odin Institute for Computational Engineering and Sciences, Stefan develops computational methods to tackle large-scale problems in science and engineering. His principal interests lie in high-performance computing and the analysis and the implementation of numerical methods for solving linear and nonlinear systems of partial differential equations. With that, let's give Omar and Stefan a round of applause.
Okay, thank you all very much. So we're really thrilled to be here and share with you the work of our team on forecasting tsunamis in real time with high-fidelity physics models under uncertainty. I know it seems impossible, right? Using digital twins. So this work won the Gordon Bell Prize. This is the team that won the prize. For those of you who weren't in the previous session or maybe don't know about the Bell Prize, this is the highest recognition awarded by ACM for advances in HPC in the context of complex scientific problems. So this was awarded in November. You heard the climate talk just before this one from Daniel. They won the climate-designated Gordon Bell Prize. So 2 prizes. You're hearing from both. Thank you. Shriram and Melinda from UT Austin, Elise, Veselin, John, and Sanyo from Lawrence Livermore. And Sanyo is right here. So you can catch us afterwards and ask us any questions that we don't address here. This is a picture of the team winning the prize. All right, so what was the case that we made? And I alluded to it in the introduction. So we're solving extreme scale inverse problems. These inverse problems have 1 billion parameters. We'll get to the specifics in a minute. They are high fidelity. So we're not giving up high fidelity models. The models themselves, a single forward run is an hour on 512 GPUs. And you'll see we have, formally, if you use today's state-of-the-art algorithms, you would have to run 250,000 times or so. 250,000 forward runs to solve the inverse problem. Now, of course, we do much better than that. We want to do everything in the Bayesian framework, so we want to quantify uncertainty in the inverse solution, and it's got to be done in real time for the application that we're addressing. So what is the application? All right, so this is, on the left, this is the Pacific Northwest. The Cascadia subduction zone extends from Northern California, so a few hundred miles north of here, 1,000 kilometers up to British Columbia, Vancouver Island here. The Juan de Fuca plate, which is an oceanic plate, is moving eastward. The North American plate is moving westward. They collide at this red line, and the oceanic plate dives underneath the continental plate. That's called subduction. That process is called subduction. So at the red line, you get this diving behavior. The oceanic plate is denser, so it's pulled by gravity and goes down. The pink region is where the two plates are stuck together because of friction. Just because they're stuck together, it doesn't mean that strain has not been accumulating, because the motion still occurs. The plates are being driven towards each other, so friction holds them in place, but strain accumulates and accumulates and accumulates. And at some point, the friction is overcome. Violent slip occurs. The two plates slip past each other. The friction is overcome. A massive amount of energy is released, and the overriding plate gets lifted upward. And that upward motion of the overriding plate lifts up a column of water. That creates gravity waves on the surface of the ocean, and those gravity waves propagate towards the Pacific Northwest, where they would inundate the coast with tsunamis of up to 30 meters, and then out west, they would propagate out to Japan and Asia, where they're much smaller, but still measurable. The last time this happened was in the year 1700, so it's been 326 years, and paleoseismic evidence suggests 43 earthquakes over the last 10,000 years. So through very careful detective work, 43 earthquakes, and if you divide 10,000 by 43, you get 250 or so, which means we're overdue. So Cascadia, which is capable of a magnitude, up to magnitude 9 rupture, is overdue. So in response to that, there are plans to instrument the subduction zone with acoustic pressure sensors that are mounted on the seafloor. And these acoustic pressure sensors, when there's the uplift that occurs during the earthquake, acoustic pressure waves are generated. These waves propagate through the ocean. The sensors measure the acoustic waves, and the idea is to take this information, solve an inverse problem to infer the seafloor motion. So the seafloor motion is causing these acoustic waves. Solve the inverse problem, infer the seafloor motion, and then once we know the seafloor motion, we can forward predict that and propagate the gravity waves towards shore and make forecasts of where the waves will strike and what the heights will be. Now, the problem is we have to do this in less than 15 minutes. So the first waves arrive in 15 minutes. We have to be very fast. So if you want to give people early warning so they can seek higher ground, this has got to be done in less than a minute. All right. So this is, if you've heard, tsunamis usually think shallow water equations. Here we're not using the shallow water equations because they don't capture the pressure transients that occur in the immediate aftermath of the earthquake. Instead, we have to use the full 3D wave propagation equations coupled with gravity waves. So we want to use the full physics, and as I mentioned, we want to quantify the solution of the inverse problem. We want to quantify uncertainties in the solution of the inverse problem and have to do so in real time. All right, so these are the governing equations. For those of you who like PDEs, the top are the acoustic wave equation in mixed form. P is pressure, U is velocity. These are coupled to the gravity waves on the surface. Eta is the gravity wave height. And the key, this is the boundary condition at the seafloor. So the normal component of velocity, this is what we're solving the inverse problem for. We're trying to infer what is the seafloor velocity. Now that seafloor velocity is a spatio-temporal field. So we've got to discretize it. We have about 2.5 million grid points in space and another 500 time steps in time. So it's a spatio-temporal representation, 2D times time. And then we have some absorbing boundaries on the lateral boundaries to let the waves propagate out because we're truncating, we're not solving over the entire planet. the wave propagation equations are implemented on top of MFEM, which is Lawrence Livermore's finite element library, using higher order finite elements. And this runs on GPUs, and you'll see all kinds of results coming up. This shows you the kind of geometry we're dealing with. It's a multi-block mesh. This is one block showing a discretization. It's kind of hazy, but you can make it out. And you can see very complex bathymetry. It's exaggerated bathymetry of the ocean. So you have to mesh all of this up, and then you patch these together, and you solve over the entire 1,000 kilometers. Okay, that's the forward problem. Now, the inverse problem. The inverse problem is, as I said, we measure the acoustic pressure at the sensor locations. Let's call that D observed. And we define something called the parameter to observable map. What that means, F, that's the map, give me the parameters, so give me the seafloor motion, that's a boundary condition, solve the acoustic gravity wave equations, extract the pressures at the sensor locations, that's the forward map. We have to do the inverse. We have to take observations of the pressures at the sensor locations, go backwards, figure out what's the seafloor motion. Okay, so this problem, unfortunately, is ill-posed. Why? Well, the observations are very sparse. You'll see the first example we have has 600 sensors covering a region of 1,000 kilometers. That's not many. The observations are noisy. And the parameter field officially is infinite dimensional, space and time. What that means is there are many different parameter fields that are consistent with the data up to the noise. You can choose many different parameter fields, and you won't see a difference within the noise in the sensors. So it's ill-posed. So we prefer the Bayesian framework. It's a very attractive, systematic way of representing uncertainty in the solution of an inverse problem, because what it says, it tries to characterize the probability that any parameter field is consistent with the data and the model and any prior knowledge you might have about the seafloor motion. Unlike the classical regularization approach, where you try to pick one set of parameters that are best fit the model in some sense, in the Bayesian framework, you try to characterize the entire distribution. All right, so what that means is Bayes' law, the posterior is proportional to the likelihood multiplied by the prior, and for the specific choice of prior and noise that we have, you get that the posterior is proportional to this expression. Exponential, the exponential of this, the argument here, which says that when the model parameters are such that the model predicts the data well, we tend to have higher probability, it's a minus sign, so higher probability. And when the parameters are close to their prior values, again, we're going to have higher probability. And these two misfits are weighted by the appropriate covariances, which represent the confidence we have in the observations and in the prior knowledge. All right, so that's the easy part. You can just write this down. The problem is, how are we going to compute this? So the thing we have working in our favor is that the inverse problem is linear. The parameters enter linearly, the dynamics are linear, and the observation operator is linear. And furthermore, if you have a Gaussian prior and Gaussian noise, that means the posterior is also Gaussian. So that helps because a Gaussian is completely characterized by its mean and its covariance. That's the easy part. So how do we find the mean? Well, we just have to solve this linear system. HM map is the maximum a posteriori point. So HM equals some function of the data, and this is the function of the data. As the data stream in, so during the earthquake, we're going to measure the data. This right-hand side gets constructed, and then we solve for the mean of the seafloor motion. The system we have to solve has the Hessian, this H, which is the Hessian of the negative log posterior, and that is equal to, its inverse is equal to the posterior covariance. So to capture the uncertainty, we have to compute this gamma post, which is the inverse of the Hessian, and then to solve the linear system to get the mean, well, we have to solve the system that has the Hessian as its coefficient matrix. So it all comes down to the properties of this Hessian. All right, so that's the easy part. You can write this down, no problem. The problem is solving it. So to solve, the first problem we have is that the dimension is 10 to the 9th parameters. I already said that. The observation dimension is 250,000, so the number of sensors multiplied by the number of time steps is 250,000. Now we have to solve this in real time. The Hessian is a dense, formally it's a non-local operator, so it's dense. And you would say, well, 10 to the 9 cubed, if I factor this, it would be 10 to the 27th operations, so that's out of the question. But if you were smarter about it and used the state-of-the-art method, which, for example, would use the conjugate gradient method, to form the parameter to observable map, you would need 250,000 adjoint wave equations, which would take 25 years on 512 A100 GPUs. And then that's just to form the parameter observable map. You'd have to do, if you're doing conjugate gradients, you'd need an F acting on a vector and an F transpose acting on a vector. So 50 years. It would take you roughly 50 years to solve this problem. All right, we don't have 50 years. We have 15 minutes. And there's some storage. You need 4 exabytes and so on. Now, you might say, this is GTC. This is 2026. Let's do a surrogate. Let's do a neural network surrogate. The problem is, first of all, you're in 10 to the 9th dimensions. Your input dimension is 10 to the 9th. Imagine how many training data you need to populate 10 to the 9th dimensions. But worse, the forward problem is hyperbolic. These are waves. They carry information with them. You don't dissipate. You don't lose information. You carry information. That's nice from the inverse problem perspective. That's a challenge from the computational perspective. What that means is there is no intrinsic low-dimensional embedding for this problem. So the manifold hypothesis that's common in AI fails here. And that's formalized into a theorem, Kolmogorov-Enwith theorem. But basically, we can't get away with a low-dimensional representation. These problems are intrinsically high-dimensional. All right, so we're left with having to work with the wave equation. What can we do? The key insight, and I'm going to have to refer you to the paper to get the really gory details, but the key insight, one of 3 key insights really, is first of all that the system is autonomous. In other words, in this case, it's time shift invariant. If the earthquake happens today, in a month, in 10 years, you'll see the same dynamics. So this parameter to observable map is time invariant to a shift, this shift tau. Okay, that's the first thing. How does that help us? Well, in this parameter to observable map, if I write this out as now at the discrete level, this square matrix here, not square matrix, this rectangular matrix, that maps the parameters. So M1 would be the parameter field at time step 1. M2 is the parameter field at time step 2. Again, the parameter field is a seafloor motion, so 2D seafloor times motion. So if I map that to the observables, so D1 would be all 600 pressure sensors at the first time step, second time step, and so on. So if I write this out, the consequence of time shift invariance is that each column looks like the column to the left, but shifted down by 1 block. Okay? So the first thing that tells you is you only have to store and form the first column in yellow. So that's the only thing we form. Everything else looks the same, shifted down and over. The second thing that you can take advantage of is the number of adjoint PDE solves that you have to solve scales with the number of sensors. So if you have 600 sensors, you have to solve these adjoint wave equations, which go backward in time, 1 for each sensor. And that's the only thing you have to do offline. Once you've done that, so you do it once, you do that, and then after that, we never have to touch the wave equations again. And then the third major recognition is that this is a Toeplitz matrix. All right, so for you linear algebra jocks, this is a Toeplitz matrix, a block Toeplitz matrix. And Toeplitz matrices, as you know, are diagonalized with FFTs. So in the end, to apply this matrix to a vector, which means to effectively do the wave propagation, we don't have to touch the partial differential equations, the wave equations. We just do this matrix vector product, which ends up being rich in FFTs and dense linear algebra. And what hardware is great for FFTs and dense linear algebra? GPUs. Okay, so this takes us from an hour on 512 GPUs to do the wave equation solution down to a millisecond, order a few milliseconds to get the same result, exactly the same result, mathematically it's exactly the same, running on the same 512 GPUs. Okay, and the last thing I'll say, so there's more to it than that. That's just the forward problem. So that's that's replacing the forward wave propagation with this block Toeplitz application, which involves FFTs and and dense linear algebra. There's some more work that has to be done offline. Like I said, we have to do the 600 adjoint wave equations. That's based on MFEM. And then there's some linear algebra tricks that we do also that allows us to take this capability to solve the forward problem rapidly and use that to solve the inverse problem rapidly. Again, I just point you to the paper. It's easier to follow there. And I just want to, before handing off to Stefan, I'll mention that this code is open source, FFT MATVEC, that does what I just said, the Hessian vector product on the fly using FFTs. So that's available, that's a CUDA code. And it builds on a number of NVIDIA libraries, cuBLAS, FFT, the direct sparse solver, distributed dense solver, communication, and so on. Okay, so Stefan is now going to talk to you about using this framework for Cascadia and how we get this to be able to do real-time forecasting of tsunamis.
All right, thank you, Omar. So to give you just a sense of the scale of the problem, Omar already mentioned we have about 1 billion parameters, but for Cascadia, so what we do is, first of all, we have to do these adjoint PD solutions. So let's look at the setup for this. So we have a spatial resolution of about 300 meters in the mesh. So these are high-order finite elements. And you have a 1,000-kilometer long subduction zone. This is a 3D mesh. Omar showed a little block of that mesh in one of the earlier slides. So you have billions of degrees of freedom defining the state of the pressure states and the velocity states of the model. Now for the inverse problem, we'll start with 600 sensors over the Cascadia subduction zone. I'll show some different examples later on. We want to do tsunami forecasts. Here we're using 21 spatial locations to give early warning estimates, along with their uncertainties, and then the inference happens for 1 billion parameters in real time. Now, to test this model, we don't have any real earthquake data from Cascadia. You saw the last one that happened there was in the year 1700. And so for that, we worked with Alice Gabriel's team at Scripps at UCSD. They have earthquake models for realistic rupture scenarios using dynamic rupture simulation with their earthquake codes using Sysol. And here's an example of that. It's a margin-wide rupture, magnitude 8.7. On the right, you see the velocity field. So that's the seaflow motion we're trying to infer in real time. On the left, the corresponding displacement field, so the seaflow uplift. And you can see it starts in central Cascadia. The rupture is propagating north and south at the same time. You see the seismic waves that are propagating outward. And the rupture continues for quite a while. It's a very dynamic process, 4 to 5 minutes of rupture time for this margin-wide rupture on Cascadia. And so this is the earthquake scenario that we're going to test our model with. First of all, we'll run the forward model that will generate synthetic data for the pressure sensors. The forward model looks like this. These are 2D slices of the 3D solution. On the right is the sea surface wave height, so the tsunami wave. The red color you see is essentially the uplifted column of water, the displaced water that comes up. And that will then propagate as a tsunami on a longer time scale onto shore and then onto the open ocean toward Japan. On the left, you see the much more noisy-looking seafloor pressure change, and that's essentially what the sensors would be measuring point-wise at their specific locations. So this is the forward model. You can imagine this requires large-scale computing. These are big models. Just a single solution takes an hour and 500 GPUs for this particular mesh. So we were lucky to get access to some of the largest computing machines in the world. 2 of those machines were NVIDIA-based systems, those 2 here. The first one is the number 8 supercomputer in the world called ALPS. It's based in Switzerland. And it features about 10,000 or so of the NVIDIA Grace Hopper nodes, the GH200s, the superchips, coming in at a system peak of about half an exaflop. The Perlmutter system, which is where most of our development has been happening, is just up the bay here in Berkeley. It's the number 30 supercomputer currently with about 6,000 A100 GPUs. So those were 2 NVIDIA systems we had access to, and of course, our goal is, and that's part of this Gordon Bell competition, is we want to show that our code performs well at the full scale of these systems. And before we go there, though, we have to make sure that we actually perform well on the single GPU, on the single chip. And this is quite tricky when you're doing these finite element computations. If you're familiar with that, finite element kernels are usually memory-bound computations. We have unstructured meshes. So these are difficult to optimize on GPUs because we're not necessarily compute-bound, even for high-order computations. And what this looks like then, you can see here. So these are the kernels for the forward and adjoint PD solution using the MFM kernels in the final element library. And the baseline that we had is the red curve here. This was on GH200. You see the number for different degrees of freedom. And the metric we care about in finite elements isn't flops, it's the throughput. Because you can write kernels that do a lot of flops but aren't necessarily getting faster to your solution. So what you care about is throughput. How many billions degrees of freedom can you solve per second, or when you do your operator application? And from the baseline that we implemented, using these different optimization techniques, I don't go into much detail here, I don't have the time for that, but we have papers on this. You can see about a 15x speed up between our baseline implementation that we started with on GH200 all the way to the most optimized implementation, which was one that fuses the different PDE operator kernels and then uses a technique we call partial assembly. So it's a nearly matrix-free operator application that only stores some data at quadrature points for the finite element integration. Now, this one, I'm really excited to show you this slide. This just got published this week as a preprint. It's work that followed to the Gordon Bell paper, and it was led by Jishun Shu from NVIDIA, one of the dev techs at NVIDIA, Ian Carlin, who was an NVIDIA developer now at Queen's University, and John Camille at Lawrence Livermore Lab, one of the MFM developers. And so what we did here is we used the already highly optimized kernels that I just showed you before, and then tried to go from native CUDA cores onto the tensor cores. And the challenge here, I just told you we have compute-bound kernels. So usually when you use tensor cores, you're thinking lower precision, tensor flops, compute-bound. But here, everything is double precision. On the Blackwell, the tensor cores actually don't give you any higher flop rate on the double precision metric. But what we can use is that tensor cores provide a way to reduce the total data traffic between the GPU shared memory and registers, and so what you end up with is sort of like a faster computation because you put less pressure on the GPU shared memory. And this is shown here, and we did this on both the Hopper and the Blackwell system, and we got about a 50% speed up or so just by these level optimizations for all of our kernels. Now, using these optimizations, these optimized kernels, we went and ran on these large-scale systems. I already mentioned Alps and Perlmutter. We also had access to El Capitan at Livermore, an even larger system. And the two common tests we do in scalability, if you're not familiar with this, is strong scaling and weak scaling. So the first slide I'm showing you here is strong scaling. In strong scaling, on the y-axis, you see what the metric that we call speed up. So we take a fixed problem size, a certain problem of a certain number of degrees of freedom in this case, and we solve it on a fairly small configuration, maybe like 100 GPUs or so. Then we increase the number of GPUs, but we keep the problem size fixed. So each GPU has less and less workload to compute, and that makes the problem difficult to scale. So ideally, what you want to see is linear speed up. That means every time you double the GPUs, you get you're doubling the speed up of the computation, getting faster computations, and you would get 100% parallel efficiency. Here, as you can see on the Alps machine, for example, we were able to achieve 91% parallel efficiency. So a very good metric, and that allows us to do a fixed problem size very quickly. We also did weak scaling. Weak scaling is the second scalability test you typically do. In this case, we have a fixed problem size per compute unit, so per GPU. And then we increase the number of GPUs, and the problem size grows with it. So ideally, you have a flat line. The runtime in your computation stays flat while you increase the problem size. And we were able to fit on both Alps and El Cap more than 1 billion degrees of freedom per GPU, giving us really large-scale runs. In the case of El Cap, the largest unstructured mesh finite element solution that has ever been computed out there. Now, you've seen these lines, and what's hidden here, again, if you haven't been part of the HPC world as much, is how much work is in each of these lines. So optimizing the code is one thing you have to, of course, do, but to actually go and compute on the full system is a very, very different kind of challenge. It's not just about computing on a single chip. There's the network you have to deal with, the I/O part. There's a lot that goes into making these systems run at full scale, and you have to remember then there's thousands, or in some cases like El Cap, tens of thousands of nodes you're running on, you just need one node to fail, and that's going to break your simulation. Let's take ALPS for an example, just to give you a sense of what this means in our case. So we have done all this work with the optimizations, and then for ALPS, we get a window in the summer, in contact with the people in Switzerland, and they tell us, okay, here you have a week to get a little bit of, familiarize yourself with the machine, make sure your code compiles, runs fine on a small number of nodes. As you do that, you show them that everything works, and then they're like, okay, let's see, right now we're training our Swiss LLM model, at some point we'll have some time though, and it's like, okay, we have time now, here's your 10-hour time block, here's the full system, now go and get your results. So this was, I was at the East Coast at the time, it was 5 p.m. in the afternoon in August, so 10 hours, so from 5 p.m. to 3 a.m., I'm sitting there the whole time. So the first hour, I'm starting, things look okay for the smaller problems, you run larger node counts, and then, things fail, of course. You're trying to figure something out. Nobody is online in Switzerland. Trying to reach the people on Slack, but they're of course sleeping. It's after midnight. Fortunately, Tsani and his team at Livermore, they were all online, so I reached out to them, and I had what ended up being the longest WebEx call of my life. I think we were on WebEx for 8 hours or so, so essentially the whole time. And what we ended up doing, we had to identify the nodes that were failing. We ran a bisection, essentially. So we split the problem into different node counts, and then try to identify the subset of nodes that was failing, and then keep going and keep going. And so in the end, I think there was 2 nodes we identified. They were, for no obvious reason, failing. They were just dumping hundreds of gigabytes of core files. Nobody knew why. But we excluded those 2 nodes. This whole process took about 3 hours, 4 hours. And then once they were out, we were able to compute, and we actually got beautiful results for this strong and weak scaling and some other kernels and some benchmarking as well. And it just ended up being a very long night. All right, so this is actually all the phase 1 computations I just showed you, the scalability and so on, so all the MFEM part. Omar mentioned the FFT-based solver and the inversion itself. So there's a number of offline steps. The computationally highest cost is in this phase 1 computation offline. In this case, the 600 sensor adjoint PD solutions plus 21 QI forecast computations took 540 hours on 500 GPUs. It's a one-time process. You do this offline before any earthquake occurs. The rest of the offline phases are fairly cheap using this FFT-based solver. It's very efficient. I mentioned about a millisecond or a couple of milliseconds, a million times faster roughly than the PDE solution. And then what's important is the real-time aspect. So the earthquake happens, we acquire the data, the sensors are measuring these pressure waves, and we want to infer the seafloor motion and forecast the tsunamis, and that now takes 0.2 seconds. So this is the speed up we're getting, and this is in comparison to the 50 years Omar showed you earlier with conventional state-of-the-art methods for doing the same solution, 0.2 seconds. Here's the solution of the inverse problem with the 600 sensors. On the left is the true, so the ground truth of the seafloor motion. On the right, you see, in the middle, you see the inferred solution. So this is the mean of the inferred solution. Remember, we have Bayesian solution, so there's uncertainty as well. But this is the mean of that posterior for the parameter field, showing you the seafloor uplift. And you can see that overall the spatial and time components are very nicely captured. What we are missing in the inference is the high frequency spatial, the fine spatial scales. And that's because Omar was talking about it. It's an ill-posed inverse problem. We have sparse and noisy data, and trying to infer these this billion-dimensional parameter field. So you're not going to be able to recover all these fine spatial scales. But this ends up being a very good reconstruction for the data we have. Here, we did tests with the sparse network. So if you go to 175 sensors, the sparse network, we still get very nice results. And then, of course, we wanted to quantify the uncertainties. That's shown here. Here, the uncertainties are shown as sort of like the standard deviation of seafloor displacements at the at the final time step. You can also visualize them in time. And of course, more sensors means less uncertainty. On the other hand, the 175 sensors, you can nicely see the structure of the uncertainties. It aligns with where the sensors are placed. It also aligns to some extent with where the continental shelf is, where's the shallower water part. And so that is something we can quantify. At the end of the day, though, we're interested in the tsunami forecast. That's really the quantity of interest. Like I said earlier, we have 21 points where we're doing this. So here, for some of those, I'm showing plots for the tsunami wave heights at point-wise spatial locations over time. And both for 600 sensors and 175 sensors, we get very nice accurate forecasts. The forecast, the mean aligns well with the truth. On top of that, you also see, I'm not sure if you see it in the back, but there's this cone around it that depicts the uncertainty in terms of 95% credible intervals of our forecasts. Now, I just showed you 175 sensors. These were kind of placed ad hoc. We just placed the sensors. As Omar mentioned earlier, Cascadia is actually lacking instrumentation. We don't have these sensors in place right now. So one of the most important questions to answer is, given the expense of putting sensors offshore onto the seafloor, how many are required to get accurate forecasts, and where do we place them given some budget that we have? And this is something that, of course, we could just try different configurations and try different things out, but in the Bayesian setting, there's a very nice way to answer these questions and analyze this problem. We call this an optimal experimental design problem, or OED. And just briefly, the rundown without the mathematics behind it, the way you can think about it is we have a set of candidate sensor locations, for example, the 600 we showed earlier, a certain budget of sensors, and then we're trying to find the optimal sensor subset within the budget that provides, in some sense, the maximum information either about the uncertain parameters, which would be a standard OED problem, or about the tsunami forecast, the quantity of interest, in which case we call it a goal-oriented OED problem. And so in the Bayesian approach, there's different ways of approaching this, but one way is you maximize the expected information gain from the prior to the posterior. So in the sense, how much information do you add? How much do you learn by observing the data? And there's ways, of course, of mathematically characterizing that information gain. Here's running a greedy algorithm for this optimal design problem in the Bayesian setting. You see the uncertainties as sensors are being placed by the greedy algorithm, and you can nicely see how the uncertainties change in the domain as the sensor placement is happening. And of course, you're not going to do the full combinatorial problem. That would be NP hard, way too many iterations, so it's a greedy approach. In the goal-oriented setting, you get a different sensor placement that's kind of visualized on the right here. So you can see the sensors are placed close to where the tsunami forecasts are happening, whereas on the left is the standard OED problem. For the last 2 or 3 minutes, I want to just show another set of follow-on results that wasn't part of the Gordon Bell yet. We've applied this framework to create a digital twin, not just for Cascadia, but for the Japan trench as well. Most of you in the room, you all remember 2011, a giant earthquake and tsunami occurred in the Japan trench. It cost many people their lives, and of course, it also caused a meltdown of the nuclear reactor in Fukushima. And following this disaster, in which the tsunami early warning was very badly done by Japan, they didn't actually anticipate this kind of earthquake and severely underestimated the tsunami risk. Japan installed large-scale sensor networks, and this is illustrated here. So one of those large networks is SNet. It's on the Japan trench. It consists of 150 stations. Those are stations on the seafloor. They have different sensors embedded, including the pressure gauges that we have been using data from. And just to give you a sense of the scale and the effort here, SNet is connected. These stations are connected by a seafloor cable. It's about 5,800 kilometers long. That's about 3,600 miles. So it's a massive effort installing this sensor network. It was done in the late 2010s. Now here, we actually have an earthquake that happened. So we have models for this earthquake models that ISIS group has been running. And you see one of the visualization of that here. On the right, again, the seafloor velocity field. On the left, the vertical seafloor uplift. And one thing you see right away is that it looks very complicated. A lot of high spatial frequencies, a lot of reflections. Part of that is because the Japan trench is very deep. It's more than 8 kilometers deep, much deeper than Cascadia. And another difficulty in this inverse problem is we don't get to place a sensor down there, right? The sensors there's practical limitations of where you can pull your cable to and place sensors. So we're trying to infer this. Using this earthquake model, again, for our forward simulation, you see the results here, seafloor pressure change on the left in the forward model and the sea surface wave height on the right. So this is what we want to be constructing in the inversion, reconstructing in the inversion. That's illustrated here. And as a last results slide before I show you the summary and highlights, here's the inverse solution. So this is still work in progress. We haven't published this yet. It's the truest seafloor normal uplift from the model on the left, and then on the right is the inversion from synthetic data generated at those 150 stations that are actually deployed in Japan. And again, similar to Cascadia, you can see overall you get a nice reconstruction of the smooth components, but not the high, the fine spatial scales of the displacement field. Here's just a highlight slide. I'm about 20, 30 seconds before my time is up here. So I'll just show you this. And then I don't have time to go through the entire list of acknowledgements, but I want to point out Christelle Pichurski from NVIDIA. She's based in France, has been a big champion of our work, really supported us in the month leading up to Gordon Bell already. So thank you for that. And here's the references to take questions, but I'm not sure. Thank you.
Thank you, Omar. Thank you, Stefan. So it is over time, but we'll take one question. One question.
So you have one data point that you're going to validate against. Is that going to be enough to actually validate your method?
So we've tested, I only showed one model. We have different models of Cascadia ruptures, many different ones.
I was referring to Tokyo, because you don't have any data for Cascadia. It's all synthetic.
That's true. So for,
They're all lies.
Yeah.
They might be true. You have truth over there in Tokyo.
Well, not exactly, because the Huku, the sensor network I was showing didn't exist when the 2011 earthquake happened. So what we really have is we have a little bit of data from that earthquake, and we've looked at that data, but it's not enough to test this model because the sensor network was deployed afterwards. So for the Tohoku, for the Japan Trench earthquakes, you're limited in that regard. So we know what kind of earthquake happened, but there's still dynamic rupture earthquake models that actually are used to generate the synthetic data because we don't have a dense sensor network that was in place back then.
Godspeed.
Okay, I don't know about you. I feel much safer when tsunami is happening. So okay, all right. Let's give them a round of applause. Thank you.